Yeah, so I have to clarify first that my title is actually was mixed up with my collaborator's title. So actually my talk title is a surprise, but it's very much related. So we're both talking about the same work, and I'm talking about the model construction. So how to construct heterotic bundles on a specific type of non-Calabi-Yau spaces. And Eric Spains will later today at 5:45, I think, talk about in more detail how you look at moduli stabilization in these models. All right, so I said, non-Calabi-Yau, so maybe I think, probably all of you know this much better than I do, but I just would like to put this in context. So just a quick review, why did we start to do Calabi-Yaus in the first place? It seems a long time ago now. So the ansatz is where we want to do physics in 4 dimensions, and we require, we want to do cosmology, and we require the 4 dimensions to be maximally symmetric. And then if you require the solution to be supersymmetric and vanishing H-flux, then what you get is Calabi-Yau, and you can relax the condition of vanishing H-flux, and then you get what is known as the Strominger system. And this turns out to be phenomenologically very attractive. So we've just heard a very nice talk on this, and I think Lara, James, and Andre, so Lara Anderson, James Gray, and Andre Lucas will be talking about this later this week. All right, so so why not Calabi-Yaus? So one common problem you get in the heterotic string is the stabilization of moduli, and the problem is, you don't have enough flux. So this is viewed in the context of type 2, where you are able to solve this problem because you are able to switch on more fluxes. So one way out of this was realized. So I've cited some works. I mean, you could cite more, of course. So if you turn on torsion in the internal manifold, you can generate extra flux, which potentially can solve this problem. So how does the setup change? So in parallel to what we had before, we just relax the condition of having 4 maximally symmetric dimensions to just having 3. And of course, what I write here is M7 is not going to be a compact space, but a non-compact space. And then we will still have 4 non-compact dimensions and 6 compact ones. However, now this will be a warped product, and so it can be shown that if you now look for a supersymmetric solution, so now you won't get a maximally symmetric 4-dimensional spacetime, but you will get a domain wall. So and that's going to be half BPS. Then you can show that what's written here is M7 has G2 holonomy. So and this is just to point out, it's very different from the G2s we heard about yesterday. So because this is a non-compact G2, and this can be achieved if the internal space, so the internal 6-dimensional space, is half flat. All right. So so now what I want to show is that it's possible to find very explicit examples where you can construct explicit models in which you can actually, in which you can compute everything you want. All right, and so first of all, we need candidate spaces, and actually there's not so many half-flat spaces which are explicitly known, and one quite convenient set of spaces are coset spaces of the form G mod H, where G is a lead group and H is some compact subgroup of the lead group. And it turns out that in dimension 6 there are exactly 4 nearly Kahler homogeneous spaces, and nearly Kahler is a subset of half-flat. And so they are these 4 cosets, and I've colored 2 of them because those turn out to be the more interesting ones in terms of physics in the end. And I also indicated what they are as topological spaces. However, as you can see already for this space, so this will be CP3, and I suppose most of you are more familiar with the other coset representation of this space, and similar for the 6-dimensional sphere. Of course, that can be also written as SO7 mod SO6. However, for what I want to do, it's quite important to use these coset representations. And the reason is that when you start doing calculations, then actually all your differential calculations will just turn out to be group theoretical calculations. And in everything you do, you want to respect this specific structure here. And also it turns out that in the other coset representations, the natural structures you construct on these will not turn out to be nearly Kahler. Okay, so, and yeah, and when I say respect the group structure, I mean that the forms which I'll write down later, they have to be left invariant under the action of the group G, so of the big group. So this will be, let's focus on this example, so this will be SU3. So now comes the main difficulty when you want to do heterotic string theory. So we want to construct bundles on these spaces. So we've just seen in the other talk how this can be done in the Calabi-Yau case, and I will present here how we do this, or how this can be done on these specific coset spaces. So this relates to work with my supervisor Andre Lucas and Cyril Matty. So for this, it is quite useful to recall that you can always view the Lie group G as a principal fiber bundle with fiber H over the base space G mod H. And then there's a well-known construction in differential geometry, which is called is a construction of associated vector bundles. So every representation of the structure group of the principal fiber bundle will uniquely define an associated vector bundle. And well, much better is that if you know a connection on this principal fiber bundle, then you will automatically know a connection on this associated vector bundle. So, and I've given you, so I've already given you another piece of information, which is that the group structure, which is defined by the coset, already gives you a natural left invariant connection on the space. So here HI are the generators of the subgroup H, and epsilon I will be on G the left invariant Maurer-Carter forms in the direction of H. However, one problem is that from a coset point of view, they're not so easy to write down. But however, if you compute the curvature, then they drop out. So that's good news. So we don't have to actually care about them too much, and this simplifies the computations a lot. So now this is very general. This works for any representation, and in particular, if we want to do string theory, we need two connections. So we need the gauge connection, but also we need a geometrical connection. And again, for the geometry, there's a natural choice, which is simply the structure just choosing the structure constants, where A and B run over the indices of G mod H, and I runs over the dimension, so from 1 to the dimension of H. So this will then play a role later in the Bianchi identity when I'm solving the Bianchi identity. And the gauge connections we will choose will be U1s, so sums of U1s, so sums of line bundles. And for this, we need to choose one-dimensional representations. And it turns out that they will be just labeled by integers. So in the specific case, SU3 mod U1 squared, there will be two integers defining every line bundle. So there will be a collection of pairs of integers which defines the model. All right, so now let's turn to actually solving the heterotic string. So this is a work which is about to appear. So well, so this was already known for some time, that the nearly Kahler structure on these cosets can be written down like this, where I've written it out for the case of SU3 mod U1 squared. The other cases look very similar, and so you get so this is the Kahler form with Kahler moduli Vi, and they will be functions of these parameters R1, R2, and R3. and and then you have the equivalent of the holomorphic 3 form in a Calabi-Yau, and that also contains these parameters. Maybe to get an intuition for the parameters, so those two forms together uniquely define a left invariant metric, and that metric is just diagonal with R1 squared, R1 squared, R2 squared, R2 squared, R3 squared, R3 squared. So, so this will be something like the radii of the internal space. So now, so this is the gravitational sector of the heterotic string. How about the gauge sector? Well, that is solved as well, but it automatically imposes a constraint on these parameters. So it turns out that they all have to be equal, which then means that two of these parameters will vanish. So this fixes two of these moduli, so two of these scalar moduli to vanish, while one remains free. Then let me turn to the Bianchi identity. So in the heterotic string, the Bianchi identity has a non-trivial right-hand side, and in general it's very hard to solve this explicitly. So at lowest order, this only imposes a constraint on the cohomology classes of the bundle. This was also mentioned in Jung's talk before. And notice that here we've written out the full Bianchi identity. So on the right-hand side, you don't have trace R wedge R, but this R minus, where R minus is built up out of the connection which includes the H field itself. So this is so there you can see that it's a bit, so it can get very complicated to solve this, since H is on the left-hand and on the right-hand side. However, so it turns out that for the examples we're looking at, such an H will solve this Bianchi identity exactly. So you don't need to make a Taylor expansion in alpha prime or anything. I mean, this will exactly solve this Bianchi identity. Where this function C here will contain alpha prime, and the parameter R, where R has nothing to do with this R, but it is the one overall remaining R you get from the Hermitian-Yang-Mills equations. And well, this is not very illuminating, so let us Taylor expand this. Now you see a bit more structure. So you see that if you Taylor expand this in the parameter alpha prime squared over R to the fourth, so something like a large volume expansion, then you see that this will turn out to be simply, so the flux H will be simply alpha prime times some constant. Of course, this constant will depend on the integers which define the bundle. Yes. However, so now there's a small subtlety. Since we are solving this at first order and alpha prime, so we're taking the action up to and including first order alpha prime, and now so now if you have a supersymmetric solution and which satisfies the Bianchi identity, that will not automatically solve the equations of motion. And in fact, if you check this explicitly, then our solution will not solve the equations of motion. However, the non-vanishing terms in the equations of motion are of order alpha prime squared over R to the fourth. So in some large radius limit, you expect to be able to neglect them. Okay, so well, yeah, so we've seen that on these spaces with the bundle construction, which I've briefly explained, it is possible to solve the supersymmetry equations and the Bianchi identity exactly up to and including first order and alpha prime. We get a non-vanishing H flux, and well, we solve the equations of motion in a large radius limit. So so let's have now a look at the basic phenomenology which we get in these models. So I mean, I have to say that we're not very far with the phenomenology, but you can say already a few interesting things. So the first is you can compute the index of the Dirac operator on these spaces, and then filter the models you get for three families. So, and this is our main discrimination of models. So we require the index of the Dirac operator to be 3. And it turns out that many models, So many models which have rank 3, 4, 5 gauge bundles and Dirac index 3 exist. So they would be potential candidates for doing real physics at some point. So now let's come back to if you remember the original motivation, which was moduli stabilization. So this will be explained in more detail in Eric's talk. So I will just briefly mention what comes out of it. So the superpotential, when you compute the superpotential in the effective four-dimensional theory, it contains this term. So this has been known for some years now, which comes. So this comes from the torsion. So these EI are torsion parameters, and now at first order and alpha prime, we also get this constant term, which is first order and alpha prime. So now this superpotential will fix all the Kahler moduli, so with torsion and H flux. However, well, as it usually happens, the dilaton stays a runaway direction, and well, you can play around with non-perturbative effects and switch on a gaugino condensate, and it turns out that this will stabilize the dilaton. Well, this has been well known from an old work by Witten. And more interestingly, if you analyze the values that you get, then you can get a consistent parameter region. So there's certain effects which work against each other, but you can get fairly consistent parameters out of it. Okay, so let me quickly conclude. As I've shown you, non-Calabi-Yau computations can provide extra flux, which gives you some more freedom in the heterotic string to stabilize moduli. It's possible to build explicit models with H flux, so at first order and alpha prime. And where there's a large list of candidates for successful phenomenology on, in particular, so this space turns out to be the richest one and the one with the most interesting models. And all moduli can be in the end stabilized at consistent values. So yeah, what's lying ahead? Well, of course, there would be a lot of work to do. In particular, I mean, you can't do any serious phenomenology without knowing the low energy spectrum. And well, this actually in general is a very hard problem in any non-Calabi-Yau compactification. And I mean, these models are very simple and easy to handle. So even if no interesting physics comes out of this, then at least one might learn something very interesting from here. And also, I mean, again, since the models are very accessible, things that are usually very hard to calculate, like threshold effects in Calabi-Yaus, become just a very straightforward group theoretical problem. All right, thank you very much for your attention.
Yeah, this is just a comment. Probably you don't know, many years ago, back in the year 1985, I think it was, I considered precisely heterotic string compactification with torsion, with H flux, precisely on those four homogeneous spaces, on those four coset spaces. So I was analyzing the field equations. I was also analyzing the gauge bundles on these spaces, or part of the gauge bundles, and analyzing the spectra and the number of families. And indeed, I also found out that this space SU3 over U1 square, which has order number 6, is the most interesting one for the phenomenology. So I did part of the things, I think, which you're
okay, you should give me the reference.
I'm happy to do it.
I'm sorry that we didn't acknowledge this.
You've bundled rank 3 to 5, so in the end you end up with some gut group, which you of course then have to break again with some equivariant structure. So do you know how to do this? And I mean, you said you're searching for index which is 3, so in the end shouldn't you then search for something that has an index of multiple of 3?
Well, so we didn't go that far, but so you're touching an important point. And one problem in these spaces is that they're simply connected, so Wilson lines don't seem to be an option. And well, we tried looking for symmetries which you can mod out, but there don't seem to be any freely acting symmetries here. So yes, so that would be a big challenge, yes.
So do you have any idea how to break the gut group in the end?
Well, so there's a construction, but well, I mean, I don't know too much about it. But if you take the rank of the bundle high enough, then you can find some diagonal U1 hypercharge in the bundle, and that can potentially break down the representations. But yeah, I mean that's one idea, but we haven't tried it.
So the flux is proportional to the hypercharge, but you don't break it.
Sorry, what do you mean?
I mean, in order to break SU5 in the end, you need something you need some flux which is proportional to the hypercharge, but then the hypercharge is broken.
Okay, I mean, you might be right. I don't know.
The thing that's normally the hypercharge is broken, but you make something else the hypercharge.
Something like a flipped SU5 to
Yeah.
oh.
Any question?
Yeah, just an easy question. Is there any way of thinking of switching off the flux and going back to Kahler? If so, what's the bundle on that? Or are these completely disconnected?
You mean switching off the torsion?
Yeah. I mean, I know it's discrete, but yeah. But in supergravity, oftentimes one starts from the Kahler and then one says, okay, one switches on fluxes, and can one go backwards and identify the spaces? Or?
There's no rigid flat metric on these spaces. Right?
Yeah. So
how would you think of that limit?
No. Yeah. I mean, one. So I think your question might be related on one of the spaces to a famous theorem. So on G2 mod SU3, which is isomorphic, or as a topological space, this is S6, and there's Chern's last theorem, which states that there is no integrable almost complex structure on G2 on S6. And Chern claimed famously that he proved it some years ago, but then he died before he could write down the whole proof. And it's, yeah. So I think doing something like you say might solve or might disprove his theorem. But I have no good answer to your question. I can only speculate. So.
You want to ask a short question?
Yeah.
Last question.
So that's what you had said. You had this Kahler form, and then you have to set two of these parameters to 0, V1 and V2 or so. Does that mean there's cycle shrinking to 0 size or something?
Well, so the no, so the volume, so V1 and V2 will be the differences of these radii, while V3, so the one which was non-vanishing, will be the sum of them. So that is something like the volume of the space.
There's not even small some divisors or some two cycles which shrink to 0 at this limit.
So I'm not quite sure if I understand your question correctly. So if you think of
the volumes are these radii, and they're all
yeah.
Okay. All right.
So yeah, I mean
The V's are not the volume.
The V's are not the volume; they're just subparameters.
Okay.
Yeah, I mean you can think of the sphere, and it will be diagonal and have the same parameter r squared like in the diagonal of the metric, and then you can squash that. And that's some old construction, and you make the parameters in the diagonal non-equal, and then vanishing of V1 and V2 would make them the same again. But it doesn't mean that anything shrinks to 0 in that sense.
Okay, there are no further questions. Running late for coffee. The other group is already standing there. So thank you very much again.